Hey everyone, welcome back. So in this video, we shall take a look at forecasting, that is predicting future time series at a future point based on the past observations. So our goal is to predict future values of a time series. So xn plus m. So m can take value 1, 2 and so on. So if m is equal to 1, that means we want to predict xn plus 1 based on the data collected up to present. So n is the data up to present, that's x1, x2 up to xn. And if m is equal to 1, that means you want to predict time series at 1 step ahead. If m is equal to 2, that means 2 steps ahead, and so on. We are again going to assume that our time series is stationary and the model parameters are known. So what do we mean by that? So in an AR1 model, right, we have phi, that is our model parameter, right? In an MA1 model, theta would be the model parameter. So we are assuming that these parameters are known. So our only goal is going to be to focus on the time series at the next time, at a future time point. So forecasting when the parameters are unknown will be covered a little bit later on in the course. So when we talk about prediction, there are different models we can use, and we are going to focus on linear prediction. So what do I mean by that? So take a note of this notation. So we want to predict xn plus m, this lower subscript. This is the point we want to predict based on n available points. So the superscript is the available data points, and the subscript is what time in the future do we want to forecast. So we will use linear prediction. That means we'll use a linear function of all of our data. So you can see this is a linear function, this is the intercept, and this is the slope. This very much looks like the linear regression that you have studied, that you probably have studied by now. So just a quick digression. So this is a linear prediction, right? So what does a non-linear prediction look like? So for example, if I want to predict x3 based on the first 2 points, that's x1 and x2, and if I want to use this function, right, then this is a non-linear function, so this is a non-linear prediction. So anyways, you won't be focusing on non-linear prediction here. So now x21 is predicting x2 based on x1, right? So this is a linear prediction, right? This is the equation that we would use. x32 is predicting x3 based on x1 and x2. So that's why we have x1 and x2 in this linear combination here. You can also say it as, call it a 1 step ahead forecast, right? Because we have data till x2 and we want to predict the next time step. So this is a 1 step ahead forecast of x3 given x1 and x2. Given x1 and x2, that means we have this data available to us. So linear predictors that minimize the mean square prediction error are called as best linear predictors, or the BLPs. So we have already looked at the mean square prediction earlier, but I did not introduce this new language. So the estimates that we get out of mean square prediction error, or minimizing the mean square prediction error, are called as the BLPs. So now suppose we have points x1 to xn, and if we want to predict xn plus m based on these n points, right, then this is a linear equation. So instead of writing this as alpha plus this, I can have this variable x naught equal to 1, and then I can combine these two terms in this one way. Okay, so I can write it as k goes from 0 to n, x naught is 1, and then alpha naught is the intercept. So this is just a more convenient way of rewriting this prediction of this linear combination. So remember the BLPs, we want to minimize the mean square prediction error, which is this. This is what we want to predict, right? We want to predict xn plus m. and xn, and the predicted value of xn plus m will be this linear combination, right? So I have this here, and we want to find out all of these alphas to minimize this error. So minimizing this function is the same as solving this. So what have we done? Again, this is repetition from what we have seen in the previous video. So we differentiate with respect to each of these alphas, right? So we differentiate with respect to alpha naught, alpha 1, alpha 2, and so on, one at a time. And then we get a system of equations. So that's what I have written here. So I've taken a derivative with respect to alpha j, so therefore I have xj here equate to 0, and of course j can go from 0 to n. So these equations are called as prediction equations, okay? So BLPs, right, are those alphas that satisfy this prediction equation, okay? So anything that satisfies this this equation is a BLP. So these are the prediction equations. And if we plug in k is equal to 0, then this is what we get, right? So remember x naught is equal to 1. So this is the equation. And now suppose expected value of this time series is mu, right? So this is mu, this is alpha naught, expectation of x is mu again. And then we combine these terms that have mu, and then we can rewrite it this way. So what we get is that the intercept is mu times this term. So if we assume that our process has 0 mean, this intercept will disappear. So 0 mean, that is, if mu is equal to 0, then alpha naught also has to be 0. And therefore, without any loss of generality from hence onwards, we can assume that our mean is 0 and the intercept is also 0. So when we look at this prediction equations, or when we try to do this forecasting, we will not be worrying about the intercept. And we know why, right? So we'll focus on one step ahead prediction. So given x1 through xn, we want to forecast xn plus 1. And we know that the best linear predictor is this linear combination. So now nothing much has changed. So I still am looking at linear. So remember, there's no intercept anymore. And we're looking at all these variables x1, x2, and so on till xn. I've only written them in a reverse order, okay? So nothing has changed. We're just rewriting things a little bit here. And instead of alphas, we're going to use these new notations. And you'll see why we're using these notations later on. So this predicted value of xn plus 1 at n, right? So this is a prediction of xn plus 1 based on the endpoints, is given by this linear combination. So what is the pattern in this here? Phi and 1 xn phi. So this n is basically how many data points we are using for this forecast. So we're using n data points. So this n's here. That's the first subscript. The second subscript, so xn is basically 1 time step back from xn plus 1, right? So 1. If you go 2 time steps back, that's n minus 1. You use the subscript 2. And n time steps back, you reach to x1, that's your first point, and then you have phi n. So there's a reason behind why we are writing these constants. So remember, this is still linear regression. The estimation and everything, it will go on exactly the same way, except that we are calling our parameters by different names. A thing to note here is that I have phi n here, and if you recall, the partial correlation stuff that we studied in the previous video, we used the same notation. And there's a reason why we use the same notation. This phi n will also turn out to be the PACF. You don't know that yet. We'll see it later on. But this phi n will also turn out to be the partial autocorrelation function. And another good thing about these coefficients is that they display their independence on n, right? So this gamma n is this matrix with all the covariances. So this is something we have used before. Phi n is collection of all of these coefficients that we want to estimate, right? We want to estimate all of these phi's, and gamma n is this vector. So we have used all of these notations before, so I won't get into the details of this. And we already know, right, from using the previous results on regression, that phi n can be written in this way: gamma n inverse this gamma. So this is capital gamma and this is small gamma. Of course, I'm assuming that this is invertible. So if I plug in this value here, so xn plus 1n is this product or dot product of this vector phi n and x, where now I'm writing these x in reverse order, right? xn to x1, right? Because we wrote this equation here in a reverse fashion. So we have this xn plus 1n is phi n transpose x. X has this reverse terms written in reverse order. Phi n transpose, we know what these are. So what is the mean square error of prediction? So we are going to denote it in this way, right? So we predicted n plus 1 based on n terms. So prediction of this n plus 1 based on n terms is the expected value of what we were trying to predict, right? So we are trying to predict the n plus 1th point, and this is the predictor, right? xn plus 1 is the predictor for this. So this is the predictor here. You plug in the value. So I plug in this formula for xn plus 1 and this is what we get. Again, we know that phi n transpose has this form. So it's a good idea to go ahead and work out these equations on your own because it can be a little bit confusing with the transpose here, okay? So phi n is gamma n inverse gamma. So phi n transpose, things get reversed. It's going to be this gamma transpose times this transpose. However, this is a square symmetric matrix. Therefore, phi n transpose is gamma n transpose times this inverse. This x remains. So you open out the square term. So you should always check this is a number, and the way in which you write this should also end up being a number. So it's important to write this transpose and to write these vectors and these matrices properly, so that the end result should be a number as well, because xn plus 1 is a number, okay? So this is a number, this is a number, the square, therefore this makes sense. You open it up, this is what you get. And now you can take this expectation inside. So this will be expected value of xn plus 1. Remember now n plus 1 is a number, x is a vector, and then you'll take expectation here, and this x transpose is going to be a matrix, right? So x is, dimension of x is 1 by n, x transpose is n by, this is n by 1 and this is 1 by n, so this is an n by n matrix, okay? So you should be careful when you write this out. In any case, on the next slide I'll show you that this expected value of this ends up being gamma n, expected value of this ends up being this should have been gamma n. There's a typo here, so this is gamma n. So things cancel out, gamma n inverse gamma cancels out. This will cancel out. Remember, there's a typo here and you end up with this. So before I end this video, I'll quickly show you how to look at this expected value of this guy and this term. So expected value of x times n plus 1. Remember, x is a vector. Its first element is n minus 1, last one is x1. N plus 1 is a number. So this, you can just open it this way. So we have the first term in x, which is xn times xn plus 1 and the expectation. Second term times xn plus 1 expectation, and so on, okay? And this is nothing but gamma 1, gamma 2, and so on. Okay, and this we are denoting by this notation, gamma subscript n. This n tells you that there are n elements in this vector. So if you want to look at XX transpose, this is X transpose, you multiply it. So this term times this term is xn. First times the second term you have here. The first element times the last one is here. For the second row, you look at the second element in this vector and then multiply it with each of these elements and so on. So what you end up is with an n by n square matrix. And now if you take expectation of this matrix is the same as taking expectation of each of these elements. So if I take expectation of this, that's gamma 0, gamma 1, and so on. Okay, so this is nothing but this vector, which is gamma n. So that is all for this video. So we have studied how a little bit about how to do one step ahead forecasting. So we'll study some other methods to again do this one step ahead forecasting, and one of those methods is the Durbin-Levinson algorithm. We'll look at it in the next video. See ya.